All right. Normally, if we were in class, I would have gone through just one problem out of each category to help you get started. Remember, adding and subtracting, you must have like radicals. Things need to look the same. And so we look at this problem. It's kind of shaded. I'm going to do this one in the middle. Basically, these radicals are not the same, but it's not too hard to make them the same if we just try to pull something out of 128 and also simplify this x to the fourth. Now, 128, it does have a perfect number inside of it. It would be a perfect cube. It would be the number 64. Now, the reason it's 64 is because I can take 64 out. It becomes smaller. It becomes its root, and that would be 4. It is going to leave behind that 2. No big deal. It's probably what is supposed to be left behind. Now, this x to the fourth, a lot of it can come out. In fact, the highest amount of x that's divisible by 3 would be x to the 3. But it also, keep in mind, is going to leave behind an x. But nonetheless, we can take out the x to the 3, and it becomes just an x when I take it out. It does leave behind an x. Now, if you look at these radicals, you see that they are the same. That's because both of them are roots of 2x. And so I can take the units that are in front and combine them together. So we're going to end up with negative 3x's of these root 2x's. I think if you flip over to the back, you'll see another problem that's shaded in. It would be this division problem, but nonetheless, it's a multiplying and dividing problem, so you do have to just have the same index. That's actually kind of nice. They're going to be the same, or at least they are the same here, so since these are both third roots, I can divide these numbers. Now I'm going to divide 108 x to the fifth and 4x squared. When you divide 108 by 4, you end up with 27. When you divide the x's, you actually subtract the exponents. And when I subtract those exponents, I end up with x to the third. Now, at this point, we kind of have to think, what else can I do? It's a third root. 27 is a perfect third power. And so all of 27 comes out to be a 3. X to the third is also all going to come out because it evenly divides with that 3. So it leaves us with just a 3x. And then I thought we'd do this problem down at the, this problem in the middle, where we have to do some creating. What's happening here is that this is a square root. This one's a cube root. And since they're not the same, what I'm going to do is I'm going to shift this to be a rational exponent. So it would look like the entire xy now to the 1/2 power. It would look like the entire 2xy now to the 1/3 power. Now, as we've done a number of times, we want to make these denominators look the same. To make them look the same is to understand that they both can turn into 6's. The reason they can turn into 6's is because that's the common denominator. Of course, to make them turn into 6's, I'm going to have to multiply to fix it. So for this first one, I'm going to multiply by 3. That's going to give me a numerator now of 3. For this one here, I'm going to have to have multiplied by 2. That'll give me a numerator of 2. Once the roots are the same, and once the denominators are the same, that really means that the roots are the same. So I'm able to write this as xy cubed, the 6th root that is, and I can also write this one as the 6th root of 2xy squared. Now, since the radicals or the indexes are both the same, we're allowed to get underneath here and we're allowed to multiply. We're allowed to multiply these two guys together. But really, before I do that, I should realize that the exponent is going to distribute to each and every one of these, leaving us with some new terms. Now, if you're okay doing this all in one step, we're going to have an x cubed over here with an x squared over here. That's going to leave us with an x to the 5th because we add the exponents. That's also going to leave you with a y to the 5th, again, because we add the exponents. And if you take careful note to this squaring, you get 2 squared, but 2 squared is the same as 4. So we can have this final answer of the 6th root of 4xy, x to the 5th, y to the 5th. Now, do the practice paper. But come back and watch the other video because I will explain or give the answers to the remaining problems. All right, now if you're watching, you should have already done the rest of the problems. Make sure you're not just listening and copying answers. So did you already do this problem? If you did, you should have found it to be pretty easy because all you have to do is add basically the 3x and 4x. That's because the radicals are already the same. So we end up with 7x's of the square root of 5x. Got to break down 24. 24 breaks down to be an 8 and a 3. The reason I'm using 8 is because 8 is going to be a perfect cube root. It's going to have a perfect cube root. So the number 8 is able to come out. It comes out as a 2. You know, there's already an x out there. What else? The 3 is left behind, and x squared didn't change. Now, in this other radical, we have a x to the fifth. You know, some of that 5, some of that x can come out. In fact, a lot of it can come out. X to the third can come out. When the x to the third comes out, it divides evenly, and it becomes just an x. So now there's an x on the outside, but there is some stuff left behind. Well, look, this 3 is left behind, and this x squared is left behind. Perfect, because that's now the same. Since the radicals are the same, we're able to add the coefficients. We're able to basically add the like terms. So we now have 2x plus x. 2x plus x is 3x, but my radical stays the same. We call it the cube root of 3x squared. Put some review questions in just to try to keep you fresh. You should be applying, or as we said, we could say that we distribute, but it's a multiplication problem. When you take that exponent, you're going to multiply 1/3 times 4. That's going to give you 4/3. You're going to multiply 3 times 1/3. That's going to give you 1. And you're going to multiply 12 times 1/3, and that should give you 4. There's really nothing else that can be done here, unless for some reason you decided that you wanted to write this x as a radical. It doesn't say that you have to, but if you were going to write it as a radical, it would be the third root of x to the fourth. There would still be this y on the outside, and there's still this z to the fourth underneath. So both of those are fine. What are you going to do first here? Are you going to bring in this 2? Well, you can, or you can add the exponents. I like to say that if you add the exponents, you get less exponents. Usually less exponents is better. So if we add 1/2 plus 2/3, in other words, if we add the exponents, now you got to make some common denominators. You're going to make a denominator of 6. That means that you multiply the top by 3. That means you multiply the top by 2. But 3/6 plus 4/6, that's 7/6. That's going to be my new exponent, 7/6. Now, at this point, I can take this 2 and I can bring it in. How do you bring it in? You multiply it. You always multiply when you have like a power to a power. And you really just multiply it to the 7. So we end up with 14/6. The thing is that 14/6 can reduce by 2's, and that leaves you with 7/3. So it's 3 to the 7/3 power. Now, if you were told to write this as a radical, you could do it. You could write it as the third root of 3 to the 7th. And 3 to the 7th, if you had a calculator, 3 to the 7th is a big giant number because it's 3 times 3 times 3 times 3 times 3 times 3. I lost track. It's 7 of those, and that gives you 2,187. Let's flip over to the back. Couple problems left to do back here. If you want to keep listening to see if you did it correctly, you are allowed when you're doing a multiplication problem to just multiply the coefficients. You are also allowed to multiply underneath, but of course when you multiply underneath, you're supposed to add the exponents. Now when I add those exponents, I end up getting x to the 5th power. And if you've been following along, we know that we're going to be able to do some interaction with these. Basically, they divide, and they completely divide. So we end up with x to the 1st power. The radical, the root, disappears. Good distributive property problem. When you distribute, you're going to multiply underneath. You get 24x squared. You also multiply underneath and you get 18x. Now, both of these are square roots, and since they're square roots, maybe we can take something out. I'm sure that you're excited to do that, but you can split up 24 to be 4 times 6. That's because 4 is a perfect number that's able to come out. It comes out as a 2. It leaves behind the 6. How about this x squared? This x squared is able to completely come out, and when it comes out, it divides and leaves us with just x to the first power, or just x. So it looks like I get a nice little 2x root 6. This 18, remember, this is a square root, so I'm going to split that up into 9 times 2. 9 is the perfect number that can come out. Of course, when it comes out, it becomes the square root of 9, which is 3. The 2 is left behind. I don't think there's anything we can do with that x. Kind of a different looking answer, but we have simplified it into smaller values. And finally, some advanced thinking where we do a little bit of switching. There are some shortcuts to this. Some of you may have noticed that what's really happening here is we're trying to switch and make the roots both be the same. As we've done a number of times, the common denominator for this is 6. If you're ready to skip ahead, you could say that this is just going to be a 6th root of 4 squared. Now, if you lost track of where those numbers came from, 6 is what the denominator turned into, and 2 is what the numerator turned into. You can kind of do the same little whoop-de-ding here with 5 to the 1/2. We can change the 2 to be the denominator of 6, but that's going to give us a numerator of 3. So I now have 5 to the 3rd power. 4 squared is 16. 5 cubed is 125. And you actually can multiply these numbers together. Since they're both underneath here, I can multiply them together. And you get one more big giant number here. I believe you get 2,000. So it's actually the 6th root of 2,000. All right, and I'll work out this last one, but be careful that everything is to the 1/4 power. Be careful that in this case it's just x squared to the 1/3 power. I would suggest that you combine these exponents together. I could write that as x to the 2/3 power. That way I just have less exponent to look at. I'm going to go ahead and change that up here just to save a little space. So we have x to the 2/3, but still I want to make these denominators be the same. I want to make them both be 12s, and in order to do that I have to multiply by 3. So now I have 3 12ths. In this case I'd have to multiply by 4, so now I have 8 12ths. The root is the same. That's good. That was the whole goal here. The root is 12. But I still have my 2x in this. Now it's to the 3rd power, and I still have my x. Of course, now it's to the 8th power. When you distribute this 3, you find out that you really get an 8x3, not 6x3. Remember, it's 8 because that's 2 times 2 times 2. But I can actually add my exponents together and get x to the 11th. 8 doesn't have anything to change with.